Dear colleague, my name Bazargeldy Khudaikuliyev. The title of my report is the following: the non-negative solutions of a second-order elliptic equation with a singular potential in a domain with a conic point. My title consists of three parts: introduction, preliminary, and the main theorem. Introduction. Let K from In, where n greater than or equal 3, be a domain with a conic point, and Pero be a ball of radius ρ, where ρ is less than or equals 1, centered at the origin of coordinates. Let omega equals to K crossing Pero, and the omega is the boundary of the domain omega. It is assumed that the boundary the omega of the domain omega is sufficiently smooth everywhere except at the origin of coordinates. Recall that a domain K is called a domain with a conic point if its boundary is infinitely smooth everywhere except at the origin thereof, and in a neighborhood of the origin, the domain K coincides with a cone sigma whose vertex is the point thereof. In a domain omega, we consider the problem 1112 of finding a non-negative function of equals, where equals is a point in In and delta is a standard Laplacian. By a solution of equation 1, we mean a non-negative generalized function distribution U such that where U belongs to L1 locally of omega and U equals C for almost all equals in the omega. We assume that non-negative function there belongs to L1 locally of omega and P of equals is a given non-negative continuous function on the boundary the omega. Here L1 locally of omega is the space of locally summable functions in omega. By the strike of omega, we denote the space of distribution. Let us introduce the spherical coordinates I omega, centered at the origin. The Laplace operator in spherical coordinates is of the form 1, 3, where delta omega is the Beltrami operator. Let lambda rho be the least eigenvalue of the Beltrami operator minus delta omega on G crossing dB rho of dB rho with the rho Dirichlet boundary condition on the crossing of the pair and let y rho of omega be the eigenfunction corresponding to the least eigenvalue lambda rho. Let the function p of equals be defined by the formula 1, 4. Let us find the function where 0 satisfying the equation 1, 5 in the sense of distribution, since the Laplace operator in spherical coordinates has the form 1, 3, the following relation 1 equals follows. We define the potential where they are all by the formula 1, 7. We are here equals to alpha multiplied by 2 minus alpha. Note that if there belongs to the segment 0, 1, then the number alpha is found from the relation alpha equals to 1 minus square root 1 minus c, and delta v belongs to L1 of omega for alpha in null in 0, 1. In the present paper, we analyze the behavior of non-negative solution of problem 1112 for the case in which the function where 0 of equals has the form 1, 7 and show that if there belongs to the segment 0, 1 and where is less than or equals to where 0, then this problem has a non-negative solution in the domain omega for any non-negative continuous boundary function p of equals, while if c is greater than 1 and where greater than or equals to where 0, then this problem does not have any non-negative solution provided that p is greater than 0. When studying the solvability and property of solutions to boundary value problems for elliptic equations, in the case when the boundary of the domain contains angular points or conical points, the method used for domains with a smooth boundary are implicable. In the case, it is impossible to smoothen the boundary with a smooth transformation. In addition, if there are conical points on the boundary, the solution of the elliptic problem may not be infinitely differentiable with infinitely differentiable right-hand side and coefficient of the equation and boundary operator. Thus, in the case under consideration, the result cannot be similar to the result related to domains with a smooth boundary. Contractors in the paper 1 consider a general boundary value problem for elliptic equation for domains whose boundary contains a finite number of conic points. The solution is considered in special spaces of function, contrastive space, having derivative summable with some weight. This space captures well the main feature of solution to such problems, which consists in the fact that the solution is smooth everywhere except for conical points, and when approaching a conical point, derivative have power law singularity. When solving a boundary value problem, the main play is to study the neighborhood of a conical point. In the paper 2, Stradinger studied the existence and uniqueness of solution to the first boundary value problem for a general elliptic equation, the local and global regularity of such solution, and some qualitative properties of solution such as the weak and strong maximum principles and proved conic inequality for elliptic equation with measurable coefficient. The first initial boundary value problem for the linear heat equation in the neighborhood of a singular point was first studied in the paper 3, and the behavior of solutions depending on the value of parameters was obtained. In this paper, it is proved that if C of n equals to n minus 2 square divided by 4, and the potential where thereof has the form 1, 8, then at C belongs to the segment thereof C of n, and where is less than or equal to where thereof in the unit pole P1, the first initial boundary value problem for linear heat equation has a non-negative solution, and for C greater than C of n and where greater than or equal to where thereof in the unit pole P1, this problem has no non-negative solution for any non-negative initial function. In the case where the base of the cylinder is a cone, similar results were obtained in 4. Note that the constant C of n is the best constant in the classical Hardy inequality, and this constant cannot be attained in the Sobolev space. This work stimulated the obtaining of interesting results on the behavior of solutions of both linear and nonlinear equations with singular potential. Similar results for elliptic problem 1112 were obtained in 5. The problem 1112 was studied in the case when the function phi of x has the form 1, 9. and it was shown that there exists a constant share of n equals to n minus 2 square divided by 4, such that if the function where the row is given by 110, then in the domain omega, the problem in question has a non-negative solution for any non-negative continuous boundary function C of equals, provided that there belongs to the segment the row C of n, and where the function where belongs to the segment the row where the row where C equals to alpha multiplied by n minus 2 minus alpha, while if C is greater than C of n and where is greater than or equals to where the row, then in the domain omega, it does not have any non-negative solution, provided that C of equals is greater than 0. Problems on the existence and non-existence of non-negative solution, both elliptic and parabolic problems, we are also considered in the paper 716 or this paper. Part 2, preliminary. Consider the auxiliary problem PM, where M equals to 1, 2, and so on, and non-negative functions where M is less than or equals to where, and the sequence where M is a monotone increasing sequence of non-negative bounded measurable function such that limit M tending to infinity, where M is equal to where for almost all equals in omega, and non-negative function Cm is less than or equals C, and the sequence Cm is a monotone increasing sequence of non-negative continuously differentiable functions uniformly converging to a non-negative continuous boundary function C. It follows from the classical theory of linear elliptic problems that problem PM has a uniquely bounded non-negative solution. The book 17, Gilbert triangle. This solution satisfies the integral equation to 1 for almost all equals in omega, where nu is the unit outward normal vector to the omega, and K is a green function of the problem 2. Moreover, the K divided by the nu is negative, and the function K is non-negative in the domain omega. Maximum principal argument show that the sequence UM is increasing in M. Next, we will give the following inequality. Lemma 2, 1. Let belongs to the segment row 1 and n is greater than or equal 3. Then for any function where in the row infinity of omega, the following inequality 2, 3 hold. We are where the row is defined from 1, 7. The proof of this lemma can be found in 9. Or this paper. From inequality 2, 3 follows that if the positive constant, if there is a positive constant, it is well known that singularities of the type belongs to a borderline case where standard theories such as a strong maximum principle and Gaussian bounds fail. Therefore, a new approach is required to investigate the existence of a solution to problem 1112. In addition, the constant C equals to 1 in inequality 2, 3 is the best, and this constant cannot be attained in the Sobolev space. Lemma 2, 2. Let I belongs to the interval 0, 1 and S belongs to the space C1 of 0, I. Then the inequality 2, 4 holds for Q greater than 2 and alpha in the segment in the interval 0, 1, where the positive constant K depends on Q and alpha is found from the relation. The proof of this lemma can be found in 12. In this paper can be found. For any non-negative function where in 0, 1 of omega r multiplying inequality 2, 4 by I square and integration over angular coordinates, we obtain 2, 5. This inequality. Part 3. The main theorem. The main result of the paper is the following theorem. Theorem 3, 1. Let the function v is non-negative if they belongs to the segment 0, 1 and v is less than or equals to v0 in the domain omega, then problem 1112 has a non-negative solution for any non-negative continuous boundary function C. Proof. Consider the auxiliary problem PM. Let us show that the limit of the sequence UM of solutions of problem PM is a solution of problem 1112. We multiply the equation in PM by expression 3, 1 3, 1. And integrating relation over omega. We are P is the cutoff function for the domain omega. The function V of equal is defined by 1, 4. Alpha is defined by equality. Then we have set Km equal to Um divided by P. After a direct calculation, we have the following equality 3, 3. Then, by assumption, inequality 3, 4 hold. Therefore, from the equality 3, 3 follows the inequality 3, 5. Using Cauchy's inequality to estimate the right-hand side of inequality 3, 5, we obtain the following inequality 3, 6. Let Pi from 0 and omega I equal to K crossing of Pi. We choose the function C as follows. Expression 3, 7. We assume that the inequality 3, 8 holds for this inequality. Then inequality 3 takes the form 3, 9. When V equal to Km degree divided by 2 multiplied by P and Q equals to 2n divided by n minus 2. From inequality 2, 4, we have the inequality 3, 10. Therefore, by using inequality 3, 10 and the Cauchy inequality, we obtain 3, 11 for this inequality, or 3, 12 for this inequality. Let the positive constant epsilon be a sufficiently small number. Introduce the notation 3, 13 for this notation. In this notation, inequality 3, 12 takes the form 3, 14 for this inequality. When by induction we obtain inequality 3, 15 because OM equal to Km multiplied by phi, we and the integral 3, 16 is convergent. The series 3 or this series is convergent because for mu greater than 1, alpha z is equivalent to 3, 9, 3, 18. Hence, we have for all z greater than or equals to 1, the inequality 3, 19, or this inequality. Moreover, the positive constant A is independent of P. Therefore, bypassing the inequality 3, 15 to the limit as v tending to infinity, we obtain the following inequality. For almost all equals in omega. This implies the following inequality. KMO equals is less than or equals to A, and UMO equals is less than or equals A multiplied by B equals for almost all equals in omega. Since the sequence is increasing one constant, K equals to the limit, M tending to infinity Km, and U equals to the limit, M tending to infinity Um for almost all equals in omega. Now let us show that where U belongs to L1 locally of omega. Take a point equals 0 in omega at which the value of U of equals 0 is finite. Then from the integral equation for the function UM of equals, we obtain 320 for this inequality. For any m greater than or equals 1, and for any compact subdomain such that at omega strike from omega such that satisfies the omega strike crossing to of the omega equals to 0. But by virtue of the strong maximum principle, there is a constant, a positive constant zero such that K of equals 0 is greater than or equal to 0 in omega strike. Therefore, for any m greater than or equals 1, the inequality 321 holds. This implies the inclusion where in L1 locally of omega. Since UM is a solution of problem PM, we have the relation 322. For any function c from in the row infinity of omega strike by taking into account inequality 321 and by passing to the limit as m tending to infinity, hence we obtain the relation 323, which implies that U of equals is a solution of problem 1112. The proof of the theorem is complete. Using inequality 2, 4 and the model iteration method, we can prove the following theorem. Theorem 3, 4, 2. Let U be a solution of problem 1112 if where is greater than or equals where 2 where 0, then for positive C for any positive epsilon and for any bounded subdomain omega strike from omega such that the omega strike crossing of the omega equals to 0, there is a constant a positive constant there, depending on epsilon at omega stripe, such that the inequality 324 holds for almost all equals in omega string, where I of omega is the eigenfunction corresponding to the least eigenvalue lambda I of the Beltrami operator minus delta omega on K stripe crossing of dpi with the row Dirichlet boundary condition on the K stripe crossing of dpi and alpha is defined by the equality alpha multiplied by 2 minus alpha equals C. Theorem 3.3. If C is greater than 1 and V is greater than or equals V thereof in the domain omega, then for positive P, problem 1112 has a non-negative has no non-negative solution. Prove. Let C is greater than 1, V is greater than or equal V thereof, and C is greater than thereof. If problem 1112 has a solution, then it satisfies the equation 325 in the sense of distribution. By multiplying this equation by the function 326 for this function and by integration the resulting relation over omega, we obtain the relation 327 for this relation. But it follows from inequality 324 that for any domain omega I from omega, such that the omega I crossing of the omega equals to zero, the relation 328 holds with the following relation or that inequality. Therefore, we have the following inequality. This implies that where there are O do not belongs to L1 locally of omega, seen by assumption where is greater than or equals where there are. This implies that where O do not belongs to L1 locally of omega as well. The proof of the theorem is complete. Remark. The problem of type 1112 arises in the study of the uniqueness of solution of the equation. Consider a linear initial boundary value problem pair, or this problem, where the potential where thereof is in the form 330, or in the form or in this form. It is well known that for here in the segment thereof say of and where non-negative function where satisfies this inequality in the domain omega I problem pair has a a non-negative generalized solution. As in 14, it can be shown that when there belongs to the interval K(n)-1 and K(n), this problem is not uniquely solvable when non-negative function, initial function U0 belongs to L2. Consider the function where defined by 31, which is the solution to the problem Q, for this problem. We are alpha plus, alpha minus, be the root of the equation 332. The function 331 is a stationary solution of the problem pair, non-negative and smooth outside the origin. It is easy to verify that where is the solution of problem Q in the strike of omega I, and the following relation hold, or this relation. Using the property of the tendency to the row of a semigroup with a generated 33, or this generated in L2, and choosing U0 is equal to where we obtain the absence of uniqueness in the space of continuous function, the solution of the problem pair. Thank you for your attention.